We're now beginning Chapter 2, or Chapter 2.1 of Physical Chemistry. Chapter 2 talks about the first law of thermodynamics. And before we get into that, we need to learn a little about mechanics. Mechanics is divided into three categories. The first is what we call classical mechanics, or Newtonian mechanics, or just Newton mechanics. This is when we deal with macroscopic particles, or objects such as bowling balls, your body, planets, etc. The main thing about classical mechanics, we're assuming that v is much less than c. Remember, v is our velocity, and c is the speed of light. So what we're saying is that our velocity is much less than the speed of light. If you've taken a physics class, modern physics class, you'll know that if you have higher, it's just harder math. Relativistic mechanics, you can talk about macroscopic particles or microscopic systems, whatever, any size. And that's what you have to do if your velocity is approaching the speed of light. Now we're talking about matter, so obviously it can't be equal to the speed of light, but it can get pretty close. And again, the math just comes out a little bit more complicated, and there's no point in doing that right now. The third type of mechanics is quantum mechanics, which we'll be doing much later in this class. Here, it actually applies to any scale system, but it's really irrelevant if you're talking about something as big as me. But at microscopic particles, namely electrons, we're going to be learning a lot about electrons. And in that case, velocity is close to the speed of light also. Now, thermodynamics, likely you're going to use classical mechanics exclusively in this class, which will simplify the math a little bit. Now, let's refresh our memory about Newton's second law. Newton's second law, we have that force is equal to mass times acceleration. Remember, mass is a scalar, but force and acceleration are both vectors. That's what the little arrow over them means. And it's capital F, lowercase m, lowercase a. Now, an important thing to remember, since they're vectors, the total force used in this formula here is just the vector sum of all the individual forces. You can have 200 different forces, but as long as you can add up to get the total force, you can still use this same formula here. Continuing Chapter 2.2 of Physical Chemistry and deriving how pressure volume work is canceled. So now we have capital V for volume, not to be confused with capital V for potential energy, and that's equal to A times L. See the previous slide for the diagram for that. So that's area times the length. We also said that length was the B minus X, and distributing that through we get AB minus AX. Now writing that in differential form, then we have the differential of volume is equal to the differential of AB minus the differential of AX. And we know that A and B are constants because A is just the area of the piston and B is just the location of the fixed end of the cylinder. So we have dV, differential of volume, is equal to 0 minus A dx. So simplifying that, solving for A, we get area is equal to minus the differential of volume with respect to X. Now, we can substitute that back into our pressure times area. We had differential of work equals pressure times area. So we had dW equals minus P, should be a minus sign here, it's not showing up very well. Okay. Oh, no, we didn't, no, we left the negative sign on the inside here. Okay, so we have pressure times our area, which is minus the differential of volume with respect to X. The dx's cancel out. So we end up with the differential of work is equal to minus pressure times the differential of volume. That is our formula for work, for any reversible process in a closed system. This is valid for any shaped container. So differential work reversible is equal to minus pressure times the differential of volume. Keep in mind though, in this class we won't be talking about irreversible processes very much. Now remember though, a reversible process is only a theoretical, an idealization. It doesn't exist in real life. For one thing, it would take an infinite amount of time. Because what you're doing is you're doing your process in infinitesimal steps, really baby steps, continuous. Likewise, you're always infinitesimally close to equilibrium. the whole idea of reversible process is you're so close to equilibrium, your process could be reversed at any time. Good luck reversing your car engine. Continuing on chapter 2.1, let's say that we have a vector system here, or a coordinate system, a space. So we have this particle with mass m somewhere in space. Notice we have x, y, and z. So this is representative of being in 3D space. So the distance, or the vector directly from the origin to our mass, we're going to call this vector r. R is our displacement vector. We're defining velocity as the derivative of r with respect to t. So that means velocity is a vector too. We're using lowercase t for time because we're going to use capital T for temperature. And that's lowercase v for velocity. Acceleration, we're defining as the derivative of that vector v with respect to t. So acceleration is also the second derivative of our displacement vector with respect to t. If you don't recognize this differential calculus notation, I recommend you take calculus before you continue this class. We're going to do a lot of calculus in this class. So we could also do this as components though. Like instead of this one r vector, we could have the x vector, the x vector, the y vector, and the z vector. So what we could say is that we have a force in the x component of force, and that's going to be mass times the acceleration in x. We could also have the force, the y component of force, and that will be mass times the y component of acceleration. And we also have the z component of force, and that's equal to the z component of acceleration times the mass. So written another way, we have the x component of force, and that's mass times the second derivative of our x position with respect to t. And then we also have the y component of force. That's equal to mass times the second derivative of our y location with respect to t. And then we also have the z component of force, which would be mass times the second derivative of our z position with respect to time. Now, one example of force that you're probably familiar with, of course, is your weight caused by gravity. Now, weight is proportional to your mass. Now, lowercase w is weight, lowercase m is mass, and here we have this means proportional to, not equal to just yet. And yes, it looks a lot like alpha that we defined in last chapter. Unfortunately, we have symbols with more than one meaning, and this is one of them. So pay attention to context so you understand what exactly does this mean right here. Now, so to make it equal, what we end up with is a proportionality constant. In this case, we're going to have g for a proportionality constant. So now we can say that weight is equal to mass times some proportionality constant. Now, in this case, the proportionality constant is called the gravitational acceleration because it's being caused by gravity. Now, here on Earth, at the surface, it's normally about 9.81 meters per second squared. Obviously, if you were to go out more decimal places, it wouldn't be exactly the same. And of course, at other locations, Mars, outer space, the moon, whatever, this number would be different. So pay attention to context. Read the problem. Continuing chapter 2.1 of physical chemistry, there are a couple of different unit systems that we'll be using in this class. One is called the MKS system. M is the length in meters. Be careful because obviously lowercase m can also stand for mass in a different context. Lowercase k is the mass in kilograms. Lowercase s is the time in seconds. And this is, of course, since force equals mass times acceleration, the unit of force is equal to newtons, where 1 newton is equal to 1 kilogram times 1 meter per second squared. The other unit system we're going to be using a lot is the CGS system. C in this lowercase c is the length measured in centimeters. Lowercase g is the mass in grams, not to be confused with lowercase g for gravitational acceleration, of course. Lowercase s is the time in seconds. And then the unit of force for this one is the dyne, which is defined as 1 gram times 1 centimeter per second squared. And of course you can convert between the two because 1 newton is equal to 10 to the 5th dynes. That one's easy enough. We'll also be using SI units, which is a modified MKS system. We'll be getting into that later. Now we're going to start talking about pressure. Pressure is defined as force over area. Now, pressure is oh, I wrote this wrong. That should be. Okay, force is a vector, but pressure and area are scalars. You're probably wondering why I didn't do it as a vector. Well, it basically comes down to it's actually the force that's perpendicular or orthogonal to the surface area. We won't be getting into that though, that's just a given. But if you've taken enough physics or math, hopefully you've learned about perpendicular forces or normal vectors, etc. Now, unit of pressure that we're going to be using, one of them, is the Pascal, which is defined as 1 Newton per meter squared. Continuing chapter 2.1, and when we talked about pressure, there are a whole bunch of different units to measure pressure. For example, we already defined the Pascal as a Newton per meter squared. 1 Pascal is also equal to 1.98 times 10 to the negative 6 atmospheres, abbreviated ATM. We also have the bar, which is 0.987 atmospheres, but that's also equal to 10 to the 5th pascals, or 750 torrs, spelled with 2 R's. Pascal is also equal to 1.45 times 10 to the minus 4 psi. Psi is pounds per square inch. If you live in the United States, you're probably familiar with that one. 1 ATM is also equal to 760 torrs, 760 torrs. Also, 1 millimeter of mercury is defined as 1 torr, because in the olden days they measured pressure with mercury barometers. Now we're going to switch gears and talk about work. Let's say that we have this box on a flat surface and we're pushing it towards the positive x direction. For that to happen, of course, our force, x, is also in that direction. So what we're talking about here is a one-dimensional system. So we don't even have to write force as a vector because it's just the x component of the force. Now this box, like I said, is moving to the right, and this distance that is traveling instantaneously is the differential of x, the displacement in x. Therefore, again, since we're talking about an instant in time, how much work is being done at any time is dw, the differential of w, the differential of work, so the instantaneous work. Now, likewise, at any point in time, the differential of work, at the x component anyway, is equal to the x component of the force times dx, the differential. So again, just think of it as force times distance equals work, but it's instantaneous. Now that is for the x component. If we do have forces in all 3 dimensions and we have movement in all 3 dimensions, then our differential of work becomes the force in x times the differential in x, plus the force in y times the differential in y, plus the force in z times the differential of z. Or put another way, you have the x component of force times the x component of movement, displacement, y component of force times the y component of displacement, and the z component of force times the z component of displacement. So the work is really just the sum of this force dx. But force can change with x. That's why we're writing the force as a function of x. So in one dimension, at all times, we always have a possibly changing force. So we add up that over time, and we get our total work. But force can be changing continuously. So really, instead of a summation, we need an integral. So work is really the definite integral from position 1 to position 2 of that force times the displacement. Now, if that force is constant over time, then of course the integral is just f of x times position 2 minus position 1. Force times the change in position, or force times distance. That's why you've probably heard that work is equal to force times distance. That's our simplified formula when we have constant force. Okay, continuing chapter 2.1 and continuing what we talk about work, we showed last time that if force is constant, then the work is equal to the force times the change in position. Work is equal to force times displacement. Now there are different units of measuring work One is the joule, which is 1 Newton times 1 meter, force times distance. With that also works out to 1 kilogram times meter squared per second squared in the MKS system. So work is obviously measured in units of energy. So for the CGS system, you have the erg, which is equal to 1 dyne times 1 centimeter. And of course, converting between the two, you have 1 joule is equal to 10 to the minus 7, or 10 to the 7th ergs. Now power, we're not going to use very much in this class, but just to mention it anyway, power measured by P, yes, same as pressure, is the rate at which work is done. So power is the derivative of work with respect to time. T is time, lowercase t is time. So if you have 1 joule in 1 second, that's 1 W, which is the watt. Continuing chapter 2.1 of physical chemistry, now we're going to talk about the mechanical energy of a one-particle system. Now, we just talked about before how work is equal to the integral of force times distance. That was in one dimension. Now you can see how if you have motion in all 3 dimensions, you do the integral separately. So we have work is equal to the integral from state 1 to state 2 of f of x dx, plus the integral from state 1 to state 2 of f of y dy, plus the integral of state 1 to state 2 of f of z dz. Be careful about the nomenclature, because if in a normal integral calculus class, this would mean substituting the number 2 and 1 in here for x, or f of x actually, but that's not what we're doing. It's state 1 and state 2, whatever values of force and distance that you'll have. Now we want to substitute in this formula for the force here, which we already talked about before. Force in x is equal to mass times the acceleration in x, but it's also mass times the derivative of velocity with respect to time, times the derivative of displacement with respect to time. Or put another way, we have the mass times the velocity in x times the derivative of the velocity of x in x. So what we're going to do here, so v is velocity, and this is our x component, and the same would be true for y and z. So using that, we have a formula for work, still the integral from state 1 to state 2 of mass times the velocity in x times the differential of velocity in x. Likewise, the integral from state 1 to state 2 of mass times the velocity in y times the differential of the velocity in y, plus the integral of from state 1 to state 2 of mass times the velocity in z as it changes with z. We actually, evaluating the integrals, that's going to give us work is equal to 1/2 of the mass times and then the Pythagorean theorem to simplify. Now this doesn't be the Pythagorean theorem yet. But anyway, so you add the x component squared plus the y component squared plus the z component squared. And then subtracting 1/2 mass times the initial x component of velocity plus the y component of velocity plus the z component of velocity squared. So we're going to define k is equal to 1/2 mv squared. So that's our kinetic energy is 1/2 times the mass times the velocity squared. So using this formula, we could substitute 1/2 mass vx squared plus vy squared plus vz squared. And so v is the total velocity in all 3 dimensions. That's where you use the Pythagorean theorem if you wanted to add those up and get the total velocity. So the work really is just the kinetic energy in state 2 minus the kinetic energy in state 1. So we have K2 minus K1. So K2 is our final kinetic energy, and K1 is our initial kinetic energy. So we end up with work is equal to K2 minus K1, or just delta K. But remember, this only applies to a one-particle system. Continuing on chapter 2.1 of physical chemistry, now we're going to talk a little about forces. There are 2 types of forces that we're going to be talking about: conservative forces and non-conservative forces. Conservative force is a force that is determined by the particle's position only. So we get force is a function of x, y, and z. Now the important thing about a conservative force is it allows us to store energy. So examples would be gravity, spring, electrical, with a coulombic force, and so on. A non-conservative force we're not going to talk really much about in this class. But if the non-conservative force depends on anything other than position, such as maybe the velocity or time. An example that you probably figured out on your own is friction, but also the tension in a rope or a cable and the muscle. Your muscle could be here, and you'd have a different force possibly. Now, both of these, though, have the same formula for kinetic energy. K is equal to 1/2 mv squared, which we did on a previous slide. Now, only conservative forces, though, have formulas for potential energy, which is capital V. For example, for gravity, it's mgh. In this case, our position xyz is denoted by h for height. Likewise, spring, the potential energy V is 1/2 kx squared. And obviously, k would be our position in that case. And then the electrical potential energy is equal to K times Q1 times Q2 over R. And in this case, R is our position instead of denoting it X, Y, Z. So just to make it official, our potential energy V is a function V of X, Y, and Z for a conservative force. Continuing on, chapter 2.1 of physical chemistry, we're going to show, so the derivative of velocity with respect to x is equal to minus the force in x, the x component of the force. Likewise, the y component of the force is equal to minus the derivative of velocity with respect to y. And likewise, the derivative of velocity with respect to z is equal to minus the force in z, the z component of the force. So f of x is the force along the x-axis, f of y is the force along the y-axis, f of z is the force along the z-axis. We have the minus sign because the force and the displacement are in opposite directions. Well, that'll make more sense later on when we talk about pressure again. Okay, so work we know is equal to the integral from state 1 to state 2 of force of x times the differential of x, plus the integral from state 1 to 2 of the force of y times the differential of y, and plus the integral of state 1 to state 2 of the force in z times the differential of z. So substituting out these formulas up here, then we have work is equal to the minus integral from state 1 to state 2 of dv with respect to x plus dv, minus the integral from state 1 to state 2 of the derivative of velocity with respect to y, minus the integral from state 1 to state 2, the derivative of velocity with respect to z, hence the differential of z. So now what we remember, dv, the total differential of v, is just the differential in v with respect to x dx, plus the differential with respect to y dy, plus the differential of v with respect to z dz. So using that, we can find work is the integral from minus 1 to 2 of just dv. Solving that, we just get minus v2 minus v1. Distributing the minus sign, we get v1 minus v2. Wait, is that backwards? Minus, well, that's equal to, yes. Remember, v is potential energy, k is kinetic energy. So the kinetic energy in state 1 minus the kinetic energy in state 2, or the potential energy, I had that backwards. The potential energy in state 1 minus the potential energy in state 2, and that's equal to the kinetic energy in state 2 minus the kinetic energy in state 1. What that's showing us, if you put all state 1 on one side, state 2 on the other side, that the kinetic energy in state 1 plus the potential energy in state 1 is equal to the kinetic energy in state 2 plus the potential energy of state 2. So this is just the law of conservation of energy as it's applied to a one-particle system. All this, remember, we're still talking about just a one-particle system. So remember, K1 plus V1, that's the total energy in state 1, and K2 plus V2, that's the total energy in state 2. So another way to say that is that the total energy in state 1 is equal to the total energy in state 2, which again is just another way of saying the law of conservation of energy for a one-particle system. All right, continuing in chapter 2 of physical chemistry, just finishing up 2.1 real quick. So be careful of the nomenclature. For example, we have lowercase d for velocity, capital V for potential energy. So you see a formula like this. This is for multiple particles now. So we have the potential energy is equal to 1/2 times the sum over I of MI/VI squared. So what this means is that the mv squared of particle 1 plus the mv squared of particle 2, 1/2 mv squared, you know what I mean? Distribute for 1/2. On the other hand, the V, capital V, potential energy is equal to a double sum here. So we have the sum of over I, and then the sum of all j greater than I of potential energy Ij. This is the reason we have to do it as a double sum like this is because the potential energy of particle 3 against particle 4 is the same as the potential energy of particle 4 against 3. So we don't want to double count. So that's what this j is greater than I means here in the second sum. And as we saw before, conservation of energy, this k plus this v is equal to a constant for our system. But we saw at the previous slide for a single particle system, and it's still true for a multiple particle system. Continuing on chapter 2.2 of physical chemistry, we're going to start to derive pressure volume work and how you calculate it. Now, there are a couple different types of work. One is just mechanical work, we talked about already the past few slides. The differential of work is equal to the x component of x dx, and so on if there were other dimensions. Now, our convention here is important. If dw is greater than 0, that means f of x and dx are in the same direction. If dw is less than 0, that means f of x and dx are in opposite directions. Now let's talk about reversible PV work, such as in a piston. I've drawn a piston here. Well, here's the cylinder. The piston's going up and down. We have pressure P coming down to hold the gas in our system. So this is a movable piston, able to go up and down. B here, this is, the fixed end of our cylinder. So L, lowercase cursive l, that's the length of our system. And then X, we have our x-axis coming down, and this is, X would be our position at the position of the piston at any time. And it's going to change over time as the piston moves up and down. Now remember, pressure we defined as the force over area. But this is a one-dimensional system, so it's going to be this pressure here is equal to the total force down divided by a cross-sectional area. I think we're going to assume it's a cylinder, but I'm going to say is mostly true for any shaped system. So length would be b minus our x position. So length would be the distance between those two, as I said before. So dw, this is our convention. If dw is positive, it's work being done by the surroundings or on the system. The reason this makes sense is because if work is being done by the surroundings or on the system, then the energy inside of the system is increasing. So if you have positive work, you're going to have positive increase in energy of the system. And if you were to do minus work, then your system would be losing internal energy. So like we said before, dw, the differential of work at any time, is equal to the x component of force times the change in the x position at any time. So rewrite that, we have pressure times the area, or dw is equal to pressure times area dx. Continuing on chapter 2.2 of physical chemistry, we talked last time about our convention of work and how positive work increases energy in the system, negative work decreases energy in the system. Along the same lines, if the differential of V for volume is less than 0, we're compressing the system. Therefore, differential of W, work, reversible, is greater than 0, which means we're doing work on the system. Therefore, volume 2 minus volume 1 is negative. Don't confuse this V with potential energy, of course. Likewise, if the differential of volume is greater than 0, which means our system is expanding, then the differential of work, reversible, is less than 0, which means work is being done by the system on the surroundings. And therefore, volume 2 minus volume 1 will be positive. Now we showed last time why the reversible differential of work is equal to minus pressure times the differential of volume. Integrating that, we get work reversible total is equal to minus the integral from state 1 to state 2 of pressure times the differential of volume, or with respect to volume. And remember, pressure is a function of temperature and volume. So that means we're going to get different possible curves when we graph pressure against volume. A line integral is one that's path dependent. So remember that if you graph pressure against volume, then your work is going to be the area under your pressure volume curve. Here's an example. We're going from state 1 to state 2 here. We're changing both pressure and volume. Notice we're going in a roughly straight line, and the area is going to be this shaded here. So that's the amount of work being done. Now let's say that we're going from the same pressure, state 1 to state 2. I didn't draw this to scale, obviously. But this time we're going to go constant volume and then constant pressure. As you can see, our work went down because we're only shading this much. And likewise, again, going from the same state 1 to state 2, if we do it constant pressure and then constant volume, you've got all this shaded. So all three of these curves that show going from the same initial state to the same final state, but they're doing a different amount of work because the area under this curve is different. And the reason the area under the curve is different is because of, like I said, pressure is not just a function of volume, it's a function of both temperature and volume. So these different curves will correspond to different temperatures. Now one thing too, when you're integrating, more steps is more efficient. I didn't show that on this curve very well, and then so likewise, if you have infinite steps, you get the most efficient curve. And finally, what that means is if you do it reversibly, you're going to get the most work done.